this session. My name is Michael Wilson, Chief Trainer for the Ghana Robotics Academy Foundation and a technologist at the Council for Scientific and Industrial Research Ghana. In our previous session, I introduced you to finite state machines and the classical control systems. In this session, I'll be introducing you to continuous time machines. Quite simple but interesting. I hope you enjoyed the previous video. If you had questions, just leave them as comments. We'll address them. Let's look at what continuous time machines are. So, in the previous example, our machine could only take one of two possible actions, either moving forward or moving backwards. We had a simple robot like this which would either move forward or backwards depending on the state of a touch sensor. We want to have something a little more complex. This time, we want our robot to trace this black line on this white tile. Now, mind you, this robot is traveling in a time domain. As it is moving, time is elapsing. So at each state in time, the robot is supposed to be able to decide the best action it should take. Now, if I look at this robot, it has been designed to have two light sensors, even though only one of the light sensors is connected to the intelligent brake, which tells me there is no way this robot is going to make use of this sensor, because signals can only be transmitted from the touch sensor connected to port 1 to the intelligent brake, and the robot can only control the two motors, one on port A and one on port B. So the robot has these options, either to move forward straight, to move backward straight, to move forward towards the left, to move forward towards the right, to move backwards towards the left, or to move backwards towards the right. So at any point in time, this robot is going to have to decide on either moving forward, turning left, turning right, or moving backwards, turning left in the backwards direction, or turning right in the backwards direction. Let's see how we can design a continuous time machine to achieve this. So here, let's do some explanation. So let's have this as our black line. And our robot is supposed to navigate this black line. We are going to start with an initial state where the robot has exactly half of the light sensor on port 1. So I turn this robot on. We want the robot to have exactly half of the light sensor on port 1 on the black line and exactly half on the white tile. Now, why are we doing this? I have to give you a little background about the operations of the light sensor. The light sensor operates on the principle of reflection, which you have all studied at school. If you don't know about reflection, I'll encourage that you attend or you get some videos or some training materials on the principles of reflection. Reflection is simply the bouncing of light rays when they hit a surface. So, as we have here, this light sensor throws lights out, and when this light falls on any surface, part of the light is reflected and part is absorbed, or possibly part is refracted. Now, the percentage of light that is reflected compared to the percentage of light that is absorbed or refracted is all dependent on the nature of the surface on which the lights were thrown to. If I take this surface, the two colors we have here are white and black. So, according to the principles of light or principles of physics, when light falls on the white surface is expected to reflect all the light that is incident on it, and a black surface is expected to absorb all the light that is incident on it. I'll test that by pointing this robot. So I place this white tile on a flat surface, and then I will mount this robot. I'll be demonstrating how to take readings later in another video. So I'll check how much reflection is coming from the light sensor when it is placed on a white surface, on the white part of the mat. And on the white part of the mat, I am recording 78% reflection. I'll move the robot to the black part of the mat, and I am recording 16% reflection. So let's look at this. This is how the light sensor is behaving on the current map that we have. We want to program the robot to make a decision as to whether it is supposed to turn right, left, move forward. How do we do this? We want our initial position to be exactly half on black, half on white. So virtually, if this is how we want to position our robot, it means exactly half of this figure, half of that figure added. In a way, the average of the two is what we are expecting if the robot is exactly in the position we want it to be. So I'll take half of this. So I would say if I have half of this, which is 8, and then I have half of this, which is 39. So I have 39, I add that to 8. So I have half of this being 39 and half of that being 8, because the half portion of the light sensor that is on the white is going to reflect light, and the half portion that is on the black is going to absorb light. When the light sensor was fully on the white, we had 78% reflection. So if it is half on the white, we are going to have half of that figure being reflected. When it was fully on the black, we had 16% reflection. So if only a half of the light sensor is expected to be on the black, we are expecting 8% reflection. So in total, if I add 39 plus 8, we are expecting 47% reflection in this initial state. Mind you, this initial state figure of 47 is very important in the principle of control systems. Why is this very important? It is until we know our preferred state that we can measure whether our system is deviating from its preferred behavior or not. Now that we know our preferred state, that if the light sensor is exactly where we want it to be, we should be recording 47% reflection. The next thing to know, so now we have our initial state, or let me call it the preferred state. I'll clean this. So, we are expecting, let's call that preferred value, which is 47. So as the robot travels in the time domain, we have to be monitoring whether the system is deviating from its state, because we are expecting that it follows the line exactly maintaining half of the sensor on the black and half on the white. To know whether the system is moving away from its desired behavior, we should be able to measure what we call the error. The error is simply the margin by which our system has deviated from its preferred value or from its preferred state. The preferred state is being measured by the sensors attached to the system. So it is the work of the engineer or you to come up with an equation that is able to capture the error value. Can I write a simple formula as this? That error is equal to the light sensor reading minus 47. Just like our chocolate factory situation. Our preferred value was 45 for the chocolate in terms of temperature. So if we wanted to know how much the temperature has risen beyond the preferred value, it's as simple as subtracting the preferred value from the sensor value. Because we are using a light sensor in this case, the light sensor value minus the preferred value will tell us the margin by which the light sensor has deviated. If the light sensor should deviate more into the black than the white, then the 47 value is going to the light sensor value is going to drop below 47, which is going to give us a negative error. So if the light sensor drifts into the black, error becomes negative. And if the light sensor drifts into the white, what happens? Your guess is as good as mine. Because white surfaces reflect more light, we are going to have a higher value from the light sensor, a value higher than 47. And when we subtract 47 from a value higher than 47, we have a positive error. That is very good for us in control systems. Now we know that our system can deviate in two directions. It can either deviate into the black or deviate into the white. And we can capture that deviation by the sign of the value of error. The magnitude of the value of error tells us the margin by which the light sensor has deviated, whereas the sign tells us in which direction it has deviated. Once we can measure the error, it is a good figure for us to decide what controls to put in place. Now, this robot is moving in the time domain, and we have control over, let's try to control the steering of the robot. Then what we can say is that, depending on whether the robot has deviated into the black or into the white, we will either have to steer the robot to the right or to the left. So steering can either move to the right or to the left, depending on the sign of the error we calculate. Now, by what margin should we steer? The magnitude of the error tells us by what margin we should steer. So in a way, we can say that if we measure error, then there is a relationship between error and steering. So can I say, or we can say that the steering of our robot varies as our error value. There is a relationship between steering and error. To convert this value, this variation sign into equal sign, we can say that steering is equal to a certain constant k times error. And it is our responsibility to experiment and come up with that constant k that gives us smooth navigation. So in the time domain, anytime our robot is moving, it will be able to calculate its steering and apply the appropriate steering in the appropriate direction because the error value is a vector quantity. We want to try programming this into our robot. And that will be our first continuous time machine to be programmed. So mind you, we have a formula that we have to build into our computing system. As we said, the robot has sensors. The sensor will feed a value into the computing unit, so the light sensor feeds a value. But how does the computing unit process this value? The computing unit uses that value to measure or calculate an error margin, which tells the system how much deviation there has, or how much deviation has occurred, and in which direction the deviation has occurred. Once that figure is measured, we know there is a relationship between that error value and how much steering we need to apply, both in magnitude and in direction. So we experiment that value of k that changes this variation from a variation sign to an equal to sign. We will call this kp, or the proportional constant. We'll be talking more about this. So which portion or which proportion of the error is required to be able to control steering? I hope you understood this principle. I've made it simpler. In our next session, we'll look at something interesting. We'll add a constant and see how the equation of a straight line applies to this time continuous or continuous time machine. I'll move on to our practical session where we'll program our robot to implement this principle. If you have any question on this, leave us a comment. Put your question in the comment section and we'll address your question. Be sure to subscribe to get updates on subsequent videos. My name is Michael Wilson, as I said, and I hope you are enjoying our sessions. Let's move on to the programming session. Thank you.